Okay, then let's move on to chapter 1. For guys who came in late, you can get the homework assignment number 1 from the course homepage. Okay, last week we talked about the requirements of computer networking, where the connectivity, scalability, and resource sharing are 3 major requirements. And we talk for connectivity, we talk about switched connectivity and routed connectivity, where the switched connectivity means the stateful connectivity, that you need to set up a connection and maintain the connection state. However, for routing, it's connectionless, and you don't need to set up a connection before you send the data. So it's connectionless and stateless. And we also talk about scalability, about the 3-level hierarchy, and how we could scale to, if we need to scale to billions of nodes, how we can do that by a 3-level hierarchy. And we also talk about the resource sharing, where the resources are either dedicated or shared. And so we introduce the concept of packet switching versus circuit switching, where packet switching appears to be the prevailing solution for resource sharing. However, even for packet switching, we still have alternative solutions for packet switching, and ATMs happen to be another solution, and it has stateful connectivity compared to the stateless connectivity of the internet, so they cannot coexist well. So ATM was given up, and then the entire world head for the connectionless connectivity until now. So these are what we covered last week, and today, after the requirement, we look at the principle or the constraints that we need to we are subject to. So this so here we will talk about some important concepts, including the bandwidth, overload, throughput, latency, jitter, and loss. Okay, these are the performance measures that we would talk about every day when you are in the networking society. And we also like to see what we should do at a control plane and what we should do at the data plane. Meaning, within to do networking, there are 2 kinds of jobs to do. One is a data plane, one is a control plane, where the control plane handles the control packet, the so-called control packet, while the data plane handles the user data packet. And the control plane is to help the data plane to better serve the users. Okay, and data plane is the plane that actually do the job, do the service. Okay, then another issue is the interoperability, that we look at what kind of, within networking, within those operations, what should be standardized, what should not be standardized. So the concept of standardization or implementation dependent will be discussed. Okay, first thing first, when we talk about the time or latency or bandwidth, we need to we need to give this example to illustrate the concept of bandwidth and the propagation time, transmission time. So if we have a 10 base T Ethernet, which is 10 megabit per second Ethernet, meaning that you can transmit 10 multiplied by 10 to the order of 6 bit per second. Okay, then 1 bit time will be 1 divided by the bit rate. Okay, 1 divided by the bit rate. That'll be 0.1 microsecond. So the transmission time for 1 bit will be 0.1 microsecond. So if this is the actual signal that is propagated, because it's a digital waveform in the 10 megabit per second Ethernet, and this is 1 bit, and 1 bit time is how much time does it need to transmit this signal? It takes 0.1 microsecond to transmit. So that's the transmission time. And another question to ask is, in the cable, what is the width? What is the width of the signal of 1 bit? For this particular bit, what is the length of the cable that it would occupy during the transmission? So during the propagation. So once you transmit that, then the signal will propagate through the cable. So you need to know what is the actual length that this signal will occupy the cable. So this cable is long, and I want to know what is the length when we see it propagating through the cable. And you can calculate this by the transmission 1 bit time. So within 1 bit time, that's 0.1 microsecond, and the speed of light or speed of signal, we know speed of light is 3 multiplied by 10 to the order of 10 meters per second. But here, the signal propagating on the cable will be slower than it propagates in the vacuum. So that will be 2 multiplied by 10 to the order of 8. So that's the speed of signal in the cable, approximately. So taking this time, the bit time multiplied by the speed of propagation, then you will see 20 meters in length. So that's 20 meters in length that you would actually see, if you can see, but however you cannot see the signal in the cable. But if you can see the signal, the square wave propagating along the cable, then you will actually see the width or the length of this square wave for that particular 1 bit will be 20 meters long in the cable. So that's the so-called the 1 bit in time and 1 bit in length. So the definition of bandwidth could be the maximum amount of data that can be handled by a system in a second. And in networking in particular, then the bandwidth will be the number of bits transmitted and contained in the distance propagated by the signal in 1 second. Okay. So we have a basic idea of the bandwidth, the transmission time, and the propagation time. Next, we like to group. So we have grouped the concept of bandwidth, propagation time, and transmission time. Next, we want to group the concept of bandwidth with overload and throughput. So by this figure, we can group these three together. So this is the overload. So as the overload increase, throughput should increase. And this will be the ideal case when you start to increase the overload, the throughput should increase. So this is like input and this is output traffic. So it should increase like this. And it will saturate at certain point. After that point, even if you continue to increase the overload, the throughput will be bounded. It will not increase anymore because you have reached the capacity or the bandwidth of the system. So bandwidth is sometimes called the capacity of the system. That'll be the bound of the throughput. And ideally, if your system works this way, then it's good enough, very good. However, in most cases, you would have system working like this. You increase the overload, but not all the overload would be transformed into throughput, because in a system like that has collision or congestion, then the input traffic might be lost and might be retransmitted. So the throughput does not grow at the same speed of overload. So you would have a curve like this, and then it would saturate earlier than the capacity bound. So in reality, it's mostly like this. And in some systems, it may grow like this one, where you have serious collision or serious congestion, that the throughput starts to drop at from certain point. And too much congestion or too much collision, then throughput will start to drop. And eventually, the throughput might be dropped to 0. Then in that case, nobody get through. Nobody get through. So indeed, there are systems working like this if they have serious congestion or collision. Mostly will work this way. So as we said, why not all the input traffic will become the output traffic, because you have collision or congestion, which would introduce packet loss. So the packet will be lost in the system. So I pump 10 megabit per second, but the output probably just 6 megabit per second. So 4 megabit per second have been lost. So that's why they don't grow at the same speed. And another concept is the latency in a system, where it could be in a node or in a link. The latency in a node and in a link. Sometimes called delay or latency, either way will be the same. So when we're talking about the delay or latency in a node, it would usually include two things. One is the queuing time, and one is the processing time. So I'm waiting for, say, in a node, the packet is mostly waiting to be processed, waiting for the CPU to be processed. And when it's my turn, I'm being processed. So my time spent in a node will have two parts. One is waiting in a queue, or one being processed. So queuing time and processing time. And then consider an MM1 system, which is a queuing system. And MM1 is the symbol representing the input is exponential traffic, and the output is exponential service time. So the input is interarrival time is exponential. Input traffic has exponential interarrival time, and the output service time, the service time to output the packet is also exponential. Then we call MM1, and that M actually stands for memoryless. Memoryless, because if you go back to your probability theory, you will see that exponential means memoryless. That means if you wait for, if the average time to wait for a bus is 10 minutes, and it's exponential, and now you have waited for 5 minutes, and I'm asking you, on the average, how much time you will still need to wait? And the answer is still 10 minutes. And that's called exponential, or called memoryless. Okay, so that's the MM1 system. And that one particular one means the number of servers. So only one server. So the MM1 system with the input exponential and the service time exponential and one server, then the delay or latency is calculated as 1 divided by bandwidth minus overload. So if I have bandwidth of 10 megabit per second and overload is 5 megabit per second, then I would get 1 over 5, that'll be 0.2. So that'll be 0.2 microsecond. So my latency will be 0.2 microsecond because I have 10 to the order of 6. And in reverse, it will be microsecond. So 0.2 microsecond, that will be my latency. So that's the way you use this formula. And there's another course called queuing theory that tell you how this formula comes from, and also some other formulas for different queuing systems. Okay, but here we don't go into that to look at how this formula comes from. But basically, this formula will give you a concept, a rough concept of the relationship between latency, bandwidth, and overload. Okay, and there's another theory by Littles. Little is the last name of the mathematician, and his theory is this. He said that if you have a system with throughput of this, say in this example, it's 1 packet per second, the throughput, and the latency is, in this example, it's 5 seconds on the average. So these are the average throughput and latency. Then the mean occupancy in the system will be 5 packets. So the mean occupancy will be 5 packets on the average, assuming no packet loss in the system. Okay, and you might say that this is a trivial theorem because I can tell if I have 1 packet per second coming in and everyone stay there for 5 seconds, then the mean number of packets in the system will be 5. However, the beauty of this, or the power of this theorem is that these are not constant. The throughput, the latency are not constant. They could be any distribution. They don't need to be constant, and they don't need to be normal distribution. They don't need to be whatever distribution. So any distribution, and if I know the mean throughput and mean latency, I can conclude that the mean occupancy will be this. So this theorem can be proved. However, we don't want to go into that. And this formula or this theorem can give you a good idea about what? About the buffer size you should allocate for a system. So if I have a system that has this kind of throughput and this kind of latency, then I can conclude how much buffer space I should allocate at least. So I can estimate the buffer size I want to allocate in the system, or the queue length. Okay, so here we grew several concepts together: latency, bandwidth, overload, and occupancy, throughput, and latency. Another thing, the latency could happen at a node or at a link. So consider the latency or the delay in a link where you are waiting for what? To be transmitted. So you have queuing time, and you also have transmission time. You want to get transmitted, and it takes time to get you transmitted. And after the data is transmitted, you need to propagate. The data need to propagate through the cable or through the space. So you have queuing time, transmission time, and propagation time. And there's a term called bandwidth delay product that would give you an idea of the maximum outstanding bit in transit. So if you take bandwidth multiplied by delay, well, here the delay stands for the propagation delay. Then you got bandwidth delay product, which is the maximum outstanding bit in transit for this particular cable. So here are two examples. One is a long fed pipe, and one is a short thin pipe. Long fed pipe means that the bandwidth is large and the cable is long, while the short thin pipe is different, thinner and shorter. And then you immediately will see that if you take bandwidth multiplied by delay, the delay here is the propagation delay, not the transmission delay. Propagation delay, then you got you got the number of bits in the cable, right? You got a number of bits in the cable. So that's the maximum outstanding bit in transit. So the maximum number of bits possible in this cable. And often when a link has a larger bandwidth delay product, it means that you need to be more careful in doing the flow control and congestion control. Once it's sent out, it's a huge number of bits. And if something goes wrong, all this will go wrong. And then you probably need to retransmit all of them. So, however, for a short thin pipe, things would be not that serious. Okay, something go wrong in the control or congestion control or flow control will not result in a serious result. However, for the long fed pipe, you need to be careful in doing those control. And as the technology improves, as the technology advances, then you will see that the bandwidth continues to grow from megabit to gigabit. And now the state of the art is 40 gigabit and 100 gigabit. 10 gigabit is in the backbone right now. And next we are moving to 40 gigabit and 100 gigabit in the backbone. At the desktop, we have 100 megabit per second, and some have gigabit interface at the desktop. So the bandwidth continues to grow at the edge and also at the core. However, the propagation time, the bandwidth delay product, the propagation time would not getting shorter. It would not, because the speed it's limited by what? The speed of light, or how fast the signal can travel within the cable or within the space. Actually, you can consider it's still sequential transmission. At a transmitter, you transmit like this, and then this. So it's sequential. And I draw this because if the bandwidth here is larger than this, it means that within 1 second you can have more bits get transmitted. Here you get last bit get transmitted in 1 second. Okay. But still, it's not transmitted in parallel. In all the networking transmitter, the design is have sequential. I mean, in a series, bit in a series, not in parallel. Not in the motherboard, computer motherboard, where you have bus, and each bus could be 16 bits in width. 16-bit wide or 32-bit wide. That's in parallel. But in networking, within the cable or within the wireless transmitter, the bits are transmitted in sequentially, bit by bit. And the way I draw this is because just to tell how many bits we can transmit within 1 second. Yes, and so the propagation time would not get shorter as the technology advances. No, because it's limited by the speed of light, and the speed of light would not change, whether it's what kind of light it is, or what. Well, it would change a little bit on different media. In the vacuum, and in the couple line, it's different. And roughly, it's 2 multiplied by 10 to the order of 8 meters per second. That's the signal propagation speed. Okay, so BDP is that would group this together. Okay, two other concepts or measures will be the jitter and loss. Here, the jitter stands for the delay variation or latency variation, meaning how smooth or how variant the latency is. And this measure is important for continuous traffic or multimedia traffic, but not that important for the pure data, say file transfer, homepage access. They don't care much about jitter, but they care much about jitter for the real-time traffic, especially for the voice over IP traffic. You want your voice over IP to be smooth, as smooth as possible. If the jitter is too high, it's okay for streaming, but not okay for VoIP. The reason is because for streaming, you can have put a jitter buffer, and the jitter buffer could be long. I mean, you could have a jitter buffer that introduce, say, 1 second delay, additional delay by the jitter buffer, which is fine for streaming, because for streaming it's one direction traffic. It doesn't bother the client if my streaming video is delayed by 1 second, as long as all my video traffic are delayed with this. Having the same delay, so it doesn't bother me if all my video traffic are delayed by 1 second by the jitter buffer, and the jitter buffer is introduced to absorb the jitter, which is fine. But if you do that for voice over IP, you got big trouble, because voice over IP require a delay within 200 milliseconds or 250 milliseconds. If your delay, one-way delay, is over 200 milliseconds or 250 milliseconds, the user will sense that. The user will sense, okay, I speak something and my peer, my friend, seems to respond slowly. And when your peer responds slower than you expect, what would happen? You will speak again. You will speak again. Because you start to doubt that your friend didn't hear your voice, so you'll repeat again. So that is not a comfortable feeling when you do a telephone session. So you cannot introduce too much delay by the jitter buffer on voice over IP, because it's two-way traffic. It's interactive traffic. But it's okay to put a jitter buffer that absorbs the jitter, that smooth out the delay. Say some delay is 50 milliseconds, some delay are 500 milliseconds. Then I introduce a delay to absorb them, and they all queue up. And when they get playback, when the video or audio get playback, they all suffer 1 second delay. 1 second delay, and that's fine for the client. Okay, so that's jitter, and we care that for voice over IP. And sometimes we can call voice over IP as the hard real-time traffic, while the streaming traffic as soft real-time traffic. Meaning the real-time requirement is not that hard; it's soft. You don't need to have very low latency, very good performance. Okay. And another major will be the loss, the packet loss. And usually we would say we would consider, say, congestion would be one cause that would introduce packet loss. So when you have congestion, then you would have buffer overflow, and the packet that suffer buffer overflow, when it joins the queue and the queue is full, then you will drop it and the packet is lost. And it might be retransmitted later on, but it might not be retransmitted depending on which protocol and which application. And another cause will be the bit error. Then because there's a bit error in the packet, and you do checksum or you do CRC, which we will discuss later in chapter 3. Then you would drop the packet. Then what would be the reason? What would be the root cause for the bit error? Mostly we'll think about the link error. So when transmit in the cable, there might be bit error due to noise interference. Or when we transmit in the open air, there might be bit error. And you will see that in the wired link, the bit error rate is very low because it's more immune to the noise and interference in the wired cable. However, in the open air, when you do the wireless transmission, the signal is very vulnerable to noise and interference. Then the bit error rate will be very high. So usually the bit error rate in the wired link is like 10 to the order -6 to -9, very low bit error rate. However, in the wireless link, the bit error rate could be 10 to the order -3, -4. So that's considered quite high, or say 1,000 higher than the wired link. Okay, that's the link error. And usually we ignore another source of error, which is the node error. And the node error is due to the memory error. And you would say that why memory could have error, and it's quite possible because you see in the internet there are many routers which are on all the time for how many years? For over, say, 10 years. And those memory hardware are very old. Well, probably not as old as 50 years, but could be as old as 10 years. And when the hardware is that old and on all the time, they might have defect in the memory already. And when it has defect due to the age for that memory, what happened? Something written in could be different from something read out. So you write this byte with this bit pattern, but when you read it out, it could be different. And that's the memory error. And there are study about those kind of memory error on the internet routers, and it's not negligible. The bit error rate for the memory error is not negligible. Not very high, but not too small. So so that's a significant part of node errors. So that would explain why we have bit error at a node and also at a link. So these are the source of the problem or the loss. Okay, so after seeing this, I encourage you to read through the book and try to combine those key measures together. What is their relationship, and what's the purpose of knowing those relationships? What we can do with those relationships, and so then you would have better feeling and better understanding about those measures. Next, we'll look at the control plane and data plane. That's it's interesting that we need to separate our jobs into different categories. And here, you want to carry packet around, and then you need to separate your operation or your job into two planes, into the control and data plane. And the purpose of a control plane is to maintain. So the keyword here is to maintain a platform for data plane to carry data. Okay, so the control plane is to help the data plane, and it's the data plane that actually do the service, which is to carry the data. Okay, and sometimes we also have another plane, which is called the management plane. So then we have a data plane, control plane, and then management plane. And in that case, then we differentiate control plane and management plane by the management plane only for administrators. For the administrator, that if the network administrator need to understand something or need to configure something, some devices, then that it would issue some command, and that command are processed at the management plane. Okay, and it's like if you look at a factory, a manufacturing factory, then the data plane are those people who are doing the manufacturing job online in real time. So if they need to go to the restroom, they need to have a solution on this. Who will take care of my job when I'm having a break? So that's the data plane. And there's a control plane. Control plane is like a manager that watch over the manufacturing process to see if there are any problem or see any adjustment needed. Say if I have within the manufacturing factory, the manager found there's a bottleneck. Okay, there's a queue in the process. Then I need to clean up I need to do some adjustment. Say I need to allocate some additional person to handle this, so that the bottleneck will be resolved. So that's the control plane. And then there's a management plane who might be on vacation most of the time, but will come to say on a weekly basis or monthly basis to review the productivity of this factory. Okay, that's the management plane. Okay, but here we do not talk about the management plane. The only place we talk about the management plane is in chapter 6 in the application layer. There's a management protocol called SNMP, Simple Network Management Protocol, then we talk about the management plan, but only in that section in chapter 6 on SNMP. Okay, for the rest of the book, we only talk about the control plan and data plan. So now you have a concept of the control plan is to help the data plan, and it's the data plan which actually does the job. And then the package processed by the control plan is only the control package. However, the data plan needs to handle all of the packets, including the control package, but mostly the data package. And in some systems, the control package versus the data package, control package probably is only 1%. 1% of the packets are control package. In some systems that have heavy control, then they might have, say, 5% control package. But usually the control package will be, the percentage will be very low. And then time scale. How much time do we need to process a control packet? And how much time do we need to process a data packet? Usually in the data packet, for the data packet, usually we are talking about the microsecond or even the nanosecond, meaning 10 to the order of -6 or 10 to the order -9 second. That's the data plan. We need to be fast, very fast. So it's like a factory that you need to be fast to handle all the products being manufactured. However, in the control plan, we don't care much about how much time. We don't care that much about how much time we need to process a control packet. Say, this is a routing message, and I like to do the calculation to calculate the shortest path. And it's okay if it takes milliseconds to do the calculation, because usually it's done in the background, not in the foreground. So we don't care that much about how fast we can handle the control packet. We can do the control plan jobs. So usually the manager does not need to be fast, but need to be smart, right? But the manufacturing workers need to be fast. They don't need to be smart. They just need to be fast. And how smart they can perform depends on the managers. And the manager needs to be smart enough to do the adjustment. Okay. And the performance, in the performance aspect, in a control plan, we care about the resource utilization, overall resource utilization. However, the data plan, we care about the throughput, how fast we can pump the packets. And the best example of the control plan operation will be the routing, while the best example for data plan will be forwarding. Okay. However, most literature do not differentiate them that much. Okay. Sometimes we misuse. I mean, we interleave or we use this term and do not differentiate them. However, I think it's better to differentiate them. Where routing stands for the shortest path calculation. You do the calculation, while forwarding means you actually forward a packet. So as you will see that the way that a router works will be it does the routing, the path calculation, which is the path calculation, or the shortest path calculation in the background at a control plan. However, and then once you finish the calculation, you need to update the routing table, and that routing table will be looked up when you are forwarding a packet. So at the data plan, I need to forward a packet. then I take the IP address, destination IP address, to look up the routing table. Okay, so I look up the routing table, and that lookup needs to be very fast. Needs to be very, very fast, and it's in the data plane. However, in the control plane, I do the calculation, and I update the routing table in the background, and that doesn't need to be super fast. Okay, but here forwarding needs to be super fast. So by this, you can differentiate the routing is doing the calculation, path calculation, shortest path calculation in the background. Doesn't need to be super fast, and it's important, still important, because if there's an error in the routing, then the routing table might have error, and then once you look up, you might forward the packet to the wrong directions. Okay, so that's the routing and forwarding, but routing and forwarding are just one basic pair of example. There are other examples at the control plane and other example at the data plane. So these are the other operation at the control plane, including error reporting. I need to do error reporting, and you will see that this is done by ICMP within the kernel of operating system. And then you can do configuration management. So you have DHCP or SNMP to do this kind of job. And then you would have some resource allocation if possible. However, in the internet, we don't do much on this. We don't do much resource allocation, but it's possible. And there's some operation at the data plane in addition to the forwarding, say classification. Okay, usually taking multiple fields in the IP packet, multiple fields in the packet, and look up to see to classify the packets. And deep packet inspection, I might need to look at the packet deep enough, deep into the application header and payload. Usually I look up, say in a router, we look up the IP header, and sometimes some device might look into IP header and also deeper header, say TCP header, and some might need to look even further, even deeper into the application header and payload. Okay, and then error control, traffic control, and QoS. These are all the data plane operation. The text has some more discussion on this. But what's the difference between error reporting and error control? Error control is about doing check error detection and correction. Error detection and correction. So if the packet is in error, I need to detect that error, and then I might drop it. And then if I need to report this error to the source, then I would trigger the control plane to do the job. Okay, I do the error detection here, and if there's an error on the packet, I drop it. And I might need to notify the error reporting so that the error reporting would notify the source of the packet, and then the source might decide to either retransmit or doing something else. Okay. So giving this overview, then let's look at this item for routing. It's not about forwarding the packet. It's not about looking up the table and forward the packet. It's about doing the calculation. I need to calculate, compute, and store the route or path or next hops of the packet. And then there are a whole bunch of issues to resolve in designing a routing scheme. It's not as trivial as you thought at the beginning. So there are issues including, should I pre-compute the path? Should I do the computation in advance, or should I do it on demand? On demand means a packet comes in, and I don't know how to forward the packet, and I do the calculation for this particular packet on demand. And of course, we don't want to do that because when the packet comes in, data packets come in, it needs to be forwarded right now and fast, super fast. So if you do the calculation at that moment, might be too slow, and you only do that at some particular environment. But in most environments, you don't want to do that. You want to have the path, the table ready already. I just need to look up. I don't want to do the calculation when the packet arrived. Okay, so I underline the choice. So here we have a whole bunch of issues, but I underline that, and for each issue there are several choices, and I underline the choices made by the internet. Of course, we'll talk about the solution in the next session, but here I just need to list them and give you a rough idea how internet might choose. So either pre-compute in advance or you compute on demand. Of course, we do the calculation in the background. That's because we do the calculation in the background. So it's periodically computed, and and updated periodically in the background. It's not on demand. And then is the calculation, the shortest path calculation give you hop by hop routing or source routing. Source routing meaning that you need to have a path, entire path, from this source to the destination. So I would need to not just compute the next hop. See, if I'm X, and there's a packet from A to B, and the packet happens to travel to me, and I'm X, router X, then should I compute the path from X to B, the entire path? No, I only compute the next hop router. If the next hop router, say, is Y, I only compute, okay, on the path to Y, on the path to B, Y, router Y should be the next hop. So I only need to decide the next hop router. I don't need to decide the entire path. So it's not source routing, it's called hop by hop routing. And how about the granularity of routing decision? Should I make the routing decision for, say, per packet? I have a routing decision for, per packet decision, meaning each packet could go through different paths. Or should it be per flow, meaning all packets within this flow will travel the same path? Or is it per source destination, meaning for the same source and destination pair, all the packets between them will travel through the same path? Or should it be per destination, for a destination host or destination network, they all go through the same path? And of course, well, if you have per packet or per flow decision, the granularity will be too fine. The granularity will be too fine to scale. Too fine to scale, meaning there'll be too many entries to maintain in the routing table. So then the decision made by the internet is per destination, especially per destination network. So for each destination network, I have an entry in my routing table. I don't have an entry for each flow or each packet or each source destination pair, but I have an entry for each destination network. So that's the granularity, which is quite coarse, not fine, but coarse. Another issue will be what is the information that you calculate your routing table from? Okay, based on what information you do the calculation? Well, the easiest way is to collect the entire map, the topology, the entire topology of the network, and then do the calculation. Or without a topology, I just in this room, we have about 40 or 30, 35 people here. And how do we know for each particular X, and we know how to reach X? How do we do that? We can each one get a map, well, of the topology, who is whose neighbor. Or we just exchange with neighbors, neighbor routers. So I have 4 neighbors. I exchange information with you four guys, and you have 3 neighbors, you exchange with them. So by neighbor exchange, then we can still do the calculation. And we will see these 2 approaches. One is the global, and one is partial by neighbor exchange in the internet. So global and partial. And you will see that in chapter 4, we'll talk about the Dijkstra algorithm. Dijkstra algorithm require the global information, while the Bellman-Ford algorithm require only the partial information exchanged from neighbors. And that we'll cover that in chapter 4, the IP layer. Okay, and yes, another thing will be the path. The path should it be shortest path, or what is the optimal path? What is the definition of an optimal path? The optimality could be shortest, widest, most robust, or something else. Here, the internet say, okay, the optimal path is the shortest path. Okay, so it's a simple idea. And shortest in terms of, mostly shortest in terms of the delay. Or another issue will be, should I maintain for each particular destination, should I maintain just one path, one single path, or multiple paths? And mostly in the internet, we only maintain the single path. However, that single path, because that single path might fail, so we need to be adaptive enough to switch over to some other path if that particular path failed. We maintain a single path, not multiple paths. Other control plane operation will be traffic and bandwidth allocation, where you can dynamically adjust the bandwidth and traffic. Well, this is fancy that if you can dynamically adjust and also the input traffic dynamically. However, and then you can reach some optimization goal. Say I want to minimize the end-to-end latency, or I want to do load balancing. These are good. However, the internet does not usually do not do that. They don't do those kind of resource adjustment on demand or dynamically. So usually it's not dynamic assignment. It's static planning. You can do this, but it's during the network planning stage, before the network deployment. Before the network get deployed, you do the planning. Before the network getting into the operation, you do the planning. You decide how much bandwidth you need at the backbone, how much bandwidth you need on the campus, how much bandwidth you need there. So those are static planning for the internet. Usually they don't, on the internet we don't do dynamic adjustment, because doing that will require the devices to be tunable. Okay. And then some operation like error, which we just mentioned, error reporting and host configuration. And at the data plane, we mentioned the forwarding is the basic example where you look up the table and forward a packet, look up the routing table and forward a packet. And it has all the issue in routing because, and so it depends on how routing resolve those issues, then it will follow. And here you care about how big the table is. So you don't want a big table, you want to be small, a small data structure for the routing table. And you need to have fast algorithm for table lookup and update. And as we will see in chapter 4 in the IP layer, you will see in internet, in the Linux kernel, the forwarding or the table lookup, routing table lookup is implemented by as an array of hash tables. So it's an array of hash tables. It's not just one hash table, but an array of hash tables. And it's fast enough, and the data structure is not too big, but still require multiple memory access and comparison. As we mentioned last week, routing table lookup is more expensive than switching, where you in routing table lookup need to do multiple memory access and multiple comparisons. However, in switching, you only do indexing, which is just one memory access, no comparison. Okay, so you care about the speed, the size here. Okay, another example would be the classification, where you classify packet into classes for specific services. So some class will get this kind of service. And the type of service will be forwarding, filtering, and encryption. Say, for some particular class of service, I need to block, I need to do filtering. Or some class, I need to do encryption. And in general, this kind of classification is done by so-called multi-field classification, that you look at several fields. So usually you would look at multiple fields to classify the packet into classes. And forwarding, you can consider forwarding as one particular example of classification, where forwarding only look at one single field. So single field classification versus multiple field classification, where forwarding only look at the destination address alone. And you have error control that does error detection and error correction. And then another issue will be whether the error control should be hub by hub or end-to-end. Well, the internet say both. We will see in the next session why we need both. And you have traffic control which does flow control and congestion control. Here why you are doing this, because you want to avoid buffer overflow or underflow. Overflow means that the queue is full, and underflow means the queue is empty. Okay, so what's the difference between flow control and congestion control? You can differentiate them by this. Flow control means that you want to synchronize the sender and receiver, so that the sender will not send too fast for the receiver, or the sender will not send too slow that receiver is waiting most of the time. Okay, that's flow control. However, congestion control deal with synchronizing a set of senders in the network. Meaning you're not talking about the pair. You're talking about a set of sources, a set of senders that has a bottleneck in the network, So that's the congestion control. So they are similar. These two terms are similar, but they are different, and we can differentiate them by this. And these are all so-called traffic control in the data plane. Within the data plane, we also have QoS, quality of service. If you need to control the quality, say how much you can send, then you would use policer. Or you want to regulate, okay, I allocate, I say you can send 10 megabit per second. And I need to either police you, or if you exceed, I need to shape your traffic. Or I even need to schedule to allocate bandwidth, say to enforce the bandwidth allocation. So these are all when we have QoS, we want to control the quality of services. Then we would put this component. And for this, we talk about this in chapter 7, which is on QoS. Okay, the final issue in this section is on the interoperability, where we're concerned about what should be standardized, what should not be standardized. Usually, you talk about what should be standardized. Things like the protocol message, the message exchange between the peers should be standardized. So we're talking about the message standardization, and the message could be for the control plane protocol or data plane protocol. So in the control or the data plane, so we need to standardize these protocol messages. And we also need to standardize the algorithms, some control plane algorithm or data plane algorithm. For example, we need to have exactly the same interpretation of a routing shortest path calculation, say Dijkstra. If we use Dijkstra, my interpretation of Dijkstra should be the same as yours. Otherwise, we got trouble. So these are the algorithms that need to be standardized. Okay, and also say we use checksum to do the error control, and checksum is a simple algorithm that you sum up the bit, the bit, say 16-bit checksum, then you sum up all the data payload and then put it into the checksum field. Then you need to agree on, say, is this ones complement or zeros complement when you do the addition. Then we need to agree upon this, and that needs to be standardized. So there are message format to be standardized, and also there are algorithm to be standardized. Okay, for this. However, there are some other that do not need to be standardized, which are implementation-dependent design. For example, what kind of data structure I would use to store the routing table? I could be use a hash table, an array of hash table, for example. And some other design might be using a tree, a trie structure. Or some might use a CAM, the hardware. So that does not need to be standardized. It's up to the vendors. Okay. Another thing will be, say, the algorithm to look up or to access this data structure does not need to be standardized either. So, say, the routing table lookup and the table itself does not need to be standardized. And these are the parts. So when you are designing a product, say, you often encounter this. Say I need to read the standard document. Say that could be RFC, that could be IEEE standard or ITU standard or 3GPP standard. I need to read the standard document and see how they define the protocol message, how they define the algorithm, how they define the protocol behaviors. And for this, I need to follow the standards. However, there are some parts that, say, the data structure, the lookup algorithm, they don't need to be standardized. And these are the parts I can design on my own. And it's that important to have your own design or to have better design. Sometimes it would determine your performance, for example. It would determine your performance, and that might differentiate from the other competitors. So when you are designing and implementing products, you need to be aware which part need to follow the standardization document, which part I have my own design. And for that particular, for some particular design, if I put some good design, I might outperform the competitor's product. And for that design, for that particular design, I might file a patent. I might submit a paper. Okay, these are the parts that you can contribute most. Okay. However, if there are some system that is, say, not standardized, say if you roll back 5 years from now, the LTE protocol or WiMAX protocol are not mature, not developed yet. So at that stage, you might have your own design of the protocol and propose to the standard committee. If you are persistent enough, then you can propose to the standard committee to compete. And if your contribution win in the committee, then your proposal will be adopted as the standard. So that's when if the protocol is not standardized yet. But if the protocol has been standardized, it's quite difficult to propose another protocol to replace the existing standard. Okay. However, there are many works that try to extend the existing protocol. So that's why RFC have so many. There are so many RFCs because each protocol might be defined by 50 or 20 or 30 RFC documents. Okay. Okay, that's interoperability. These are the constraints we need to work with or work under